So we got new definition. We're going to find out today what is a determinant of a matrix. So we've already learned what an identity matrix is. That's the one where along the diagonal, and it has to be that diagonal, along the diagonal you have all ones. An identity matrix are always square matrices, so they won't change the dimensions of what you're multiplying. It doesn't mean that the other matrix that you're multiplying has to be a square matrix, but you have to make sure that the identity matrix is always a square matrix with ones along the diagonal. The determinant, which we don't know what it is yet, but I'll tell you that the determinant of identity matrices are always 1. So we're going to find out what is a determinant, how it helps us with inverses, and then how to calculate the value of those determinants. So here is the formula for figuring out the determinant. And you can figure out sometimes a determinant is shown by the words det in front saying find the determinant of the following matrix. And sometimes they use what seems like absolute bars instead of the matrices brackets to say find the determinant. So if you have a bunch of numbers like here, you multiply a times d. Those ones you multiply, of course, you get a times d. And then you multiply the other diagonal, b times c. I did that one in red because that one you're always going to subtract. In fact, this is the way that I remember my formula for finding the determinant, because you always take one diagonal and multiply it by the other diagonal. The diagonals that's going backwards, sort of that red arrow sort of seems like it's going backwards, that's how I remember that I have to subtract that one. So it's just some strategies for helping you remember what the determinant is. So same thing here. Multiply this diagonal, that's positive, multiply that one, and then subtract it, and you get your determinant. So that's some number. So we'll start off with just using our formula and figuring out. Again, by memorizing all those letters, I find it hard to remember. Well, it's much easier to think, okay, I want to multiply along this diagonal. 4 times 2 is 8. Multiply along this diagonal. 3 times negative 3, negative 9. And so I would have 8 minus the negative 9 and get 17 as a determinant for the first one. Same thing for the second one. 6 times 6, 36. Negative 4 times negative 9, 36. 36 minus the 36 gives you 0. So one of these has a determinant of 17, the other one has a determinant of 0. What we're going to find out shortly about determinants is the fact that this one has a determinant of 0 is significant. Well, they're both significant, but they're significant for different reasons. The 17 is significant, the 0 is significant, but when you get 0, something bad happens, and when you get other numbers, something good can happen. So something bad can happen with 0, right? You can only find the determinant of square matrices. It doesn't make sense to find the determinant of anything that's not a square matrix. So far, we've only got a formula for a 2 by 2 matrix. And here, we find out that matrices that have this determinant of 0, we give them a special name called singular matrix because it does not have an inverse. So some numbers can't have an inverse. And if it can't have an inverse, then it won't be solvable. Okay? So now we've got another formula that we could, as you can see, easily memorize. The determinant of a 3 by 3 matrix can be found by taking this value, A, and then multiplying it by the determinant of that. Then you subtract B and multiply by the determinant of DG, these ones here and these ones here. Basically what's happening is you're taking out the column that goes along with that number across the top and using the other ones to determine the determinant. And similarly, when we get to C, across the top, you would take the determinant of the ones that aren't in that column. Again, I never memorize this formula because you can use diagonals just like we did before, okay, to figure out the determinant. And this is how the diagonals work. Erase these lines temporarily and redraw them. What we can do, whereas there's only the 2 diagonals in a 2 by 2, as far as starting things off with our 3 by 3, we just rewrite the first 2 columns again. Because then our positive diagonals, there's one going to be starting with A, multiply those numbers together. One starting with B, multiply those numbers together. And one starting with C, multiply those numbers together. All of these numbers will be positive and you'll add them up. Going backwards, first diagonal will be here, multiply those ones together. Second diagonal will be here, multiply those ones together. And the third diagonal here, multiply those together, add those all up, and that's what you're going to be subtracting. And if you do the blue minus the red, you'll get the determinant, which is a lot quicker, in my opinion, than writing out the formula and figuring out the mini determinants along the way and using the formulas all the way through. So we'll do this first one together and then I'll get you to try B on your own. So here's our positive values. First of all, I'll rewrite rewrite the first 2 columns again. 2, 1, 2, negative 1, 2, 1. 2 times 2 times 2 is 8. 0, 4. Add those up, you'll get 12. Backwards, 4 times 2 times 2 is 16. Plus 0, plus a negative 2. So here we have 14. Here we have 12. And so 12 minus 14 gives us a determinant of negative 2. So I'll get you to try part B. All right, check what you got. Do you guys get 30? Excellent. So 3, negative 2, 4, 0, 1, negative 2. Diagonals are 0 plus 0 plus 12. And over here, 12 minus 30 plus 0. And you'll get 12 minus a negative 18, which gives you 30. Or maybe you saw the 12 and the 12 would cancel out and that you'd just be left with the negative 30 there subtracting that. Either way. Now, there is something, if you're wondering if this is on a calculator part, we can find all of this stuff with our calculator as well. So take out your graphing calculators. We are first going to go to matrix and we'll enter in this 3 by 3 that we just figured out was 30. So 3 by 3. And when you have a matrix already in there, you don't have to delete things. What you can do is just type over top and work from there. So we got 3, 0, 3, negative 2, 1, 5, 4, negative 2, 0. So now I've got that matrix typed into there and some useful operations that we can find. Now if we go to our matrix menu, if I clear everything out here, go to our matrix menu, there is, we've been using the names and we've been using the edit, but we haven't done any math, and there's a whole bunch of math that you're allowed to do with your matrices. The first one is determinant. So we can go determinant and then go back to matrix and choose matrix A and push enter, and it tells us that it's 30 as well. The thing that sometimes happens is you don't go back to the main screen before that, and so then you start doing math within your matrix, and that can be a problem. But other than that, we can find determinants of matrix using that way. Some other things that are in there, we've also got the transpose. If you wanted to do the transpose, second matrix, math, the T is the transpose. That takes, you have to put your matrix in first, right? Remember the transpose, just switch the rows and columns. It's not hard to do, but there it's done for you. Notice that our first row of 303 is now our first column of 303. And one of the things that we're going to figure out later, and we actually cannot do it with the matrix that we have right now, but let's go math, second matrix. I'm just going to edit our 3 by 3 one that we had and make it a 3 by 4. Just put some random numbers in there. 5, 7, 2. Okay. So now we've got 5, 7, and 2 in there, and I'm going to go back to my main menu here, and I'm going to go second matrix, math, and I'm going to go all the way down until it has not just ref, but ref. And that stands for reduced row echelon form. Okay? So you're going to remember that? Reduced row echelon form. And if we do that, now that I've put a 3 by 4 in there, second matrix A, look at that. It changes the first set into an identity matrix, and it changes the last bunch into some new numbers. Now, if we want to know what actually happened there, what did we do? We just said, what was my original matrix here? I had 3, 0, 3, negative 2, 1, 5, 4, negative 2, 0. And I put some random numbers in there. 5, 2, 7, was that what I put? Let's just pretend that's what I put. It doesn't matter right now, because you'll get the idea in a second. What we just did by having this put in, we just solved the system of equation that would say 3x plus 0y's plus 3z's, that's a fancy z, is equal to 5. And negative 2x plus 1y plus 5z is equal to 2. And 4x's minus plus negative 2y's plus 0z's is equal to 7, what would x, y, and z be to make that work? Well, x would have to be 0.06. Y would have to be negative 0.867, and z would have to be 1.6. Oh, but Mr. JR, I don't like working with fractions, so I'm going to just go math, change my answer to fractions, and it changes our matrices. Now we know that it was 1/15, negative 13/15, and 8/5 for our answers. Yes? Yeah, just a second.